Yeah, welcome to the second part of our practical lecture 6.1. Today, understanding OpenMP parallel programming. This is really one of the ways how you do high performance computing. We had MPI in the past lectures, which is really about distributed memory programming. And now OpenMP, we have learned in the first part of this lecture and also in lecture 6 is a complete different way of programming a computer, a supercomputer, meaning directly via the access to shared memory. So you have a shared address space where you can write and read variables from and do interesting parallelization approaches by so-called work sharing constructs. And we will go into some of these work sharing constructs now in detail. We'll give some demonstrations about them, and then also see a bit more from the methodology, how you would now combine this with some, let's say, problem to solve. Of course, here as part of the lecture, as we have just 40 minutes roughly together, it's basically very simple problems, but they still carry the essence of understanding essentially what you want to do with the work sharing constructs, why it's so simple to use OpenMP for it, because it automates essentially a lot in the process. And this is quite a benefit of using OpenMP, apart from the fact that it's an open standard, so to speak. It's really on all the HPC machines around the world. So once you have programmed a parallel program in OpenMP, and you can port it then surely to some of the other HPC systems in the future. So let's review a little bit what we said is the work sharing construct idea. Also, this we had already in lecture 6. So just a quick reminder here as part of the parallel, basically of the practical lecture here. Again, the key idea here on the fork for the do and for the for loops here is essentially, of course, the iterations. So you will see that many times loops have some independent parts of it, which can be very beautifully parallelized. And I will give an example later, where essentially the different iterations of the loop can be then executed in parallel on the different threads. It's also a way of data parallelism, if you want, right? You have just different chunks of an array, maybe that you just put on different threads and they iterate over this part of the array. Sometimes we recall or basically say to this a chunk size. So when you have an array of 1,000, you maybe have a chunk size of 100, and then you would basically use OpenMP to really go through the chunk size then and so on. But this is really, of course, an application domain aspect of it. Then the different sections are important. So here we can break the big work basically that maybe comes from the top into different really separate and discrete sections. So, and each of these sections, of course, then executed by one thread. And also there could be some threads that are not involved. That could be basically also an idea of functional parallelism that we had in lecture 3. So if you want to have, let's say, in different areas of your code, different functionality, because then it's not anymore the same. Here in the loop, you still do the same idea what you do within the loop. But of course, the iterations essentially in the loop are then parallelized. This is different in the sections. So here we do completely different things within the sections, what I will program in these sections. So it's another way of saying, another idea of parallelization. And then, of course, here, which of course here has to be really reviewed from case by case, is then a single which really serializes a section of the code that could be very critical to do so. But we learn also later with critical sections, this is also another idea of maybe doing something similar, more easy, but there could be ways why you want to have a single section. So let's go and think about the data parallelism a little bit when we think about the loop parallelization. And this was already something we had in lecture 3 as an example in pseudocode, that assuming here you have essentially an interesting loop. Interesting means for us, it's actually independent from the other iterations. I repeat, the iterations here are really independent from the other iterations. What do I mean by this? So the previous result of any for loop or do loop here is not affecting the arrays that we see here. We of course iterate over this E here, basically from 1 to 1,000. And actually we just take another array B at the same index and multiply it with a constant. So in order to do this, you can immediately see that all of these 1,000 iterations can be done completely in parallel. So what I can do if I would have, let's say, one processor here that is doing the work, I can split it up to two, right? To just do it from 1 to 500 and then start again from 501 up to 1,000. And the result is the same because you remember it's shared memory. When I use this, I have still the same location of the array. All I changes of course the index. So I write in the same idea the shared memory, and I can do so, and by this of course significantly increase the time for completion here. So this means this T2, what we have here by this two processors, which are essentially two threads working on this, is smaller than T1 doing it alone. And here the idea is really thinking nicely parallelizable. Individual array elements, these are independent from each other, and that's why it works so beautiful in this particular example here. So let's put that to a real example that we have here in practice. Again, basically we have the same independence. If you remember, when you want to basically have here essentially within a loop just going through the arrays and A and B, and you want to essentially then create C out of it, you basically want to do this across different threads. Then what you all have to do is basically just having a couple of pragma statements to get this happening. And this is what we will review here a little bit. Firstly, we have to think about that, of course, we have a big parallel environment or parallel region, right? And this is something where we start here with this parallel region that should be essentially sharing the variables A, B, C, and the chunk. However, the private E, which is the loop index, should be private to each of the local threads, right? So each of the thread would have their own E, but they share the A, B, C, and chunk. So chunk could be meaning here the number of work items I really want to work on, right? You see here N, maybe the whole array is 1,000, but I want to work on it in a 100 chunk size. Meaning when you think about our schedule that we also learned in lecture 6, this would be the chunk sizes, and I would have two options here of getting through with this chunk sizes in the overall array, static and dynamic. And the difference is that in static, I always assign the same order of the threads, while in dynamic, as soon as one is completed, you see here T1 was probably completed earlier, directly gets assigned again and work item and so forth. And T4 is 3 times. So really depending on the time to completion, it will be reassigned dynamically based on the chunk size. Here we see the idea of doing this then in the different arrays. We basically have here the number of threads that we get, how many threads we see, and that work on the addition is that basically then shown in parallel. And you also see explicitly, I don't parallelize this explicitly, not any of this. Right, so this is automatically just by putting the pragma statement or the sentinel in front of the loop, and in combination with this construct, I just basically do nothing spectacular as I would have done maybe an MPI with send receives. Here, one pragma statement will take care of the loop parallelization, and I even don't specify how many threads. This is basically coming out of course, our environment variable. So let's see how this action, this basically in action, a little bit when I demonstrate it. We have here essentially the advanced for loop example that I prepared for you a little bit. Also here is everything very similar that we had already on the slide. You can imagine basically that's the same source code here. Again, the chunk size, defining it here as constants, but reusing it. We have the parallel region, which specifies private E. So the index of the loop will be private for each of the different threads, but we don't say also how many threads we're executing here. And here's a beautiful statement when you think about the for loop, that no matter what happened here, it's independent from all the other loops, right? Iterations. And this makes it really a nicely parallelizable problem for which OpenMP is just perfect to use. And here you have a submit script that is actually then the complementary part we need. As you remember, we would have 8 threads. I just defined this here as an example to show you we don't have to have 4 or 16. We can have 8. We can have different numbers. And here our executable that I don't compile again. I have already compiled it. So for you, just as information, this would be the executable. So let's see what happens if you submit it. Of course, QStudied. And again, you will see it's a very simple example, very quickly completed. And so let's look on the output. What would be inside of this? Just have to wait, I think, a little bit. Here's the one coming. And then do more on it, and we will see essentially that this was the number of threads was basically 8 times executed with this print statement. Also what we essentially thought would happen, and also said again, it's actually 8 overall. So it's exactly like the source code. I also put it inside, but it shows you that this loop was not now with one process or with one thread executed. It has 8 threads working on the loop, but how they actually did the chunking and so on, I just roughly defined. All other things is actually done then by the program environment of OpenMP. So here's another example. I was saying you giving some trouble, and we have to talk about it. Why? Essentially, we talk here about a so-called critical region that is sometimes required. Now think about a point where you want to maybe have this shared variable x that you have here, shared by all in the parallel region, and you essentially want to write in it something new, but you also want to read at it. Right? So this statement assigns a write and essentially at the same time read. Now, when you do this statement, think about that what will happen. Depending on how quick one thread is, it will either already have basically +1, in another thread received it. So that makes it 2, or it basically was reading it just before the write was happening. So it remains maybe 0 and it's just 1 now in the process here. So this is a really critical condition. We say it's a race condition of variable x here. And this is, of course, in shared memory. So this variable x is, in a way, for everyone accessible and for everyone readable, writable. And this could lead to big problems if you have larger, let's say, programs really or applications, because critical regions or these race conditions can be then really hard to debug sometimes when you don't think about it. Let me give you also there a small demonstration. We will do 2 demonstrations here to really fully understand this. So when we go to the critical example, we can now see that we have essentially these 2 options. The first one is, of course, doing it maybe wrong. So we go to the critical example. You see here, it's essentially commented out, right? This pragma OMP critical statement. So in other words, this will be now 8 times executed if you specify the number of 8 threads, for instance. And always I have the race conditions at each of these threads around x, which should be written, but also read at the same time. And then, of course, I give out the number of x after the parallel region, which is probably always very much different. So we want to compile this because we have essentially, of course, changed the source code, right? So we have to basically do this. We know how to do it. GCC-F OpenMP. We want to specify how it's called, critical example, and we use for it critical example.c. Could be some warnings. This is not so important for you right now here in the course. It's more making the code beautiful. More important for us is now what happened to this critical region, right? We have also now thinking about the job script, an idea of specifying here 4 different threads. That's fine enough for us, and using this critical example. However, when we think about our idea around the variable now, we didn't protect it, right? So it stands alone in the shared memory space for every of these 4 threads to use, to write, to read at any point in time. And there's no protection. There's completely race conditions happening on this variable. And if you see, the job is probably run and executed, finished by now, and probably will be coming with an output very soon. And what we will see now is probably not what we expect, that everybody of the threads would do it just once. Here we have this number 4, basically, but it could be also different when we think about essentially doing this off coding. So when we do the critical example, or basically remove it, just want to make sure that we do this again. We can do remove critical example. So now the executable is really gone, and I recompile it. I check the critical example, see it's still commented out. That's very important for us. So then I recompile it. That's fine. It's just a warning. And then I SPatch it with a submit critical example. Wait for it to happen. Already completed. And we wait for another output. So let's see what the other output will be. Now we have suddenly a 3. So we had a 4, we had a 3. So you see, it's not any more consistently. We cannot assume that this will happen very nicely. Now, when we do the other way around and we want to protect it and we have 4 threads, we basically assume there would be always 4, right? So this should be in a way then deterministic and always happening if we protect it. Now it's unprotected, so we have to go in the source code, remove our comment out section here to make it again a proper pragma statement, right? The pragma statement saying OMP critical, protecting only this one, but the important one, because that's where the x happening. We have x equals 0. And if you remember, the critical was really in a way sequentializing. It makes a sequence out of these 4 threads. So only one thread at a time can execute this now. And this will be important because now we can see that when this is happening sequence after sequence after thread, we assume there will be 4. And this all the time, and not sometimes 3 and sometimes less, sometimes 4. So this is something what we will basically expect. And when we do this, of course, we have to touch the source code. We have to compile it again. That's now an important part of it. Again, you will see this, and sometimes it's also good to just remove the executable so that you be sure that it's recompiled. Sometimes there's a test of if that it's still existing. But once we have done this, now we change the executable to something where we have the pragma statement out. We can SBatch it, because essentially in the batch script, we didn't change anything, right? So it's still basically the critical example, the same application name, but of course it was now compiled with this pragma statement in. And now when you qstat it, it will be probably also very much, executing very quickly. And then we can see and look at the output file. And we will have 4. Now this is a surprise, not really. No, we have assuming this. And when we now SBatch it 3 times, we will still assume, because we always use 4 threads, also the next that will come there in terms of output. In a moment, you see all of them are just finished right now. We can look on the old ones we just created and submitted. They have all 4 inside, no 3, nothing up and down. And this is an important construct, this critical. We have the same that I just essentially demonstrated with the synchronization construct of critical already here also in the slides. Of course, think about now we have done 2 times this example. So the first example, we really left it unprotected, right? Commented this pragma statement out, which makes it just a normal comment. So it's not anymore a compiler directive. You see this nicely in the color coding here. So this is really a compiler directive. This is not. This is just a comment like any other. So no OMP critical here. This exposes X to the race condition on it. So basically 4 threads that go into this parallel regions will have full write and full read access at any moment where they can access it, and as they work on it in parallel. But the shared memory space is of course not parallel. It's just 1x, right? Shared X space here. Then basically you have this race conditioning happening. So what we did for protecting it was in the part, what we said here, essentially then putting away the comments and having a complete, fully pragma statement again, a sentinel, which actually is protecting with the critical this race condition. In the end, there's no race condition anymore possible, because this ensures that only each thread at a time, one by one, one after another, can actually execute this. This is very important to understand. You also see that we didn't change anything on the job script, interesting enough. It's just the same executable. So here we just had to recompile because we changed really here the commenting in and commenting out, which is important because we're talking here about a compiler directive that this is. And of course, this has an influence if it's existing or not once you compiled it. So much for the synchronization construct. I think it's also very powerful if you think about it. It seems to be very easy from this particular example, but now think about always when you see these examples, normally would have a much bigger code. You would have an application code in some of the domain sciences. You would have many different parallel regions, potentially also intertwined with MPI message exchanges if you go across the nodes for hybrid codes. So in the end, these simple message constructed here, the simple OpenMP, constructs here are simple, but you would combine them and would add more and more. You just don't have only one loop. You maybe have also a loop and a critical section. And now from the critical section, we maybe advance to a thread private. So what is the thread private? Thread private is a very beautiful construct, which means that if you have some variable that should, remain across the different parallel regions, just to keep it safe, and not being dropped. Again, what we have said is like when we have something like this here, pragma or MP parallel, and as an example, this block should be then here, of course, done in parallel by all the different threads. We know by now this now. But here have a private B and a thread ID. The thread ID is clear to be private, but here the B is essentially like any other variable and seems to be a little bit, misplaced because I just have it for each of the different threads in private. In other words, once these threads, let's say, are not anymore existing, if you remember, after the fork comes a join, and then the master thread is just working and doing all the serial work or whatever it is here. So essentially these two values, the thread ID and B, would be lost because the parallel region is gone. So whatever I wrote here in B, with the thread ID, for instance, will be not anymore existing. While, however, the thread private A and X here, in the overall parallel regions around it, will make sure that A and X are actually not private to each of the thread, but is more, let's say, a global variable space, which basically means that this could sustain then and survive the different parallel regions we have. So, and another part is interesting thing is to put dynamic threads off. But the more interesting part really is then the second part here, right? We had this first parallel region, which does something, and then the master thread does some serial work again. And then we entered the second parallel region. And here we say again, OMP parallel private, the thread ID, which is just to identify our number of threads. And when we are in this region, we now want to give out all the A, B, and X, which we actually assigned in the first part. You remember, A was assigned, B, and X. And essentially want to just reuse the values here and give them out, combined with our new thread ID. Now, by doing this in the second, let's say, parallel region, we see a couple of things. Firstly, we don't redefine A, B, and X, right? This was done in the first one. Okay, that's clear. But we also notice that actually A and X is still or was defined as the thread private. So here we assume that actually there should be still values for A and X because we defined them as thread private. While B was really just a private variable here in the first block, which means we don't know what happened with it, so to speak. It's a lost value. Because we don't reassign it here, we also would expect that this should be probably 0 uninitiated or uninitialized. So when we now execute this and making the example, we assume that essentially all would have their values, A and X, but B essentially is lost. So let's go into the thread private example shortly. Everything which I had on the slide is here in practice, also in the source code. Again, you have this assignment in the first block here over here where we assign the different variables. We define some way here the thread private on the top, that A and X, B is missing, that's important. but it's private. But unfortunately, private only for the first one. And even if you would have it private for the second one, it would make a difference because B is lost and not kept alive after the collapse or the join, if you want, of the first parallel region. So in the second parallel region, we get the output, which is then a bit sad that we have a lost B. So, and when you now think about the submit script, there's no surprises really. It's looking very similar like the other ones. So this is something which is of course here interesting. Just realize here I maybe have a small error of the name. It should be not the critical example anymore. It is the thread private, but this is really a kind of small bug here if you want. It has nothing to do really with the functionality. It's more a naming, which you should keep up to date. But you know, essentially we want to aspect it here and see that we probably will have a problem with B. So when we look at this and QStat it, it's a very simple job, should be already basically completed. Then when we look on the output, that is basically around that time here now, then we see essentially exactly what we talked about. We have thread 0 in the first parallel region. Everything is nice because A and B are just assigned the thread ID. And then I do some multiplication for X, which is not so important to understand what. But in the second region, we directly see the bug here, or the problem, right? It's not really a bug because we programmed it that way. We said thread private is just A and X, and B is it not anymore. So we just have zeros here saying that B is uninitialized at that part, which is a parallel region 2, and exactly what we also thought would happen. And of course, this is all also in your slides. That you basically have here as a complementary. You see again, B is properly defined essentially here in our first parallel region. And then basically it doesn't matter also from the ordering of the different threads. As you know, we're giving here something on the printf out, which means there's also, let's say, a bit race condition of when do you get to the printout, because this is essentially a sequential aspect. But here we see that even no matter how you can order the threads, B will be still remaining, let's say, a 0 because it is not a thread private variable. So this has shown you clearly, I think, the idea of the thread private variable. So let's move forward. And you see more and more that essentially OpenMP lives from all of these different statements that you would combine in an application, right? So of course, each of those are basically similar and, you know, very trivial at some point in time. But the heart and complexity comes usually of combining all of this and then, of course, integrating also domain application parts of it, physical formulas. You want to do something in parallel, which is maybe not just adding an array. So it's maybe much more a multidimensional array. So you would have to basically much more put thinking in all of these different aspects when you have a real production application. Here's another interesting clause example. I put it in because it has some commonalities with something you already know from MPI reduce. If you remember, MPI reduce was putting not only the message, let's say a collective message of reducing, but also then doing some added function on it. So basically we call it an operator, right? There's some operations which are already defined, like multiplication, summation, minus, max, min, and so forth, that you can use while doing the same thing here in OpenMP, right? Instead of now doing the collective messages we know in MPI and do an MPI reduce or all reduce and so on, we do here basically a reduction clause, as it's called. And this is here indicated by this interesting statement, putting the reduction plus over the variable result. So that means that this pragma statement, OMP parallel for, will be, of course, a parallel for loop, split it up in different chunks, again, as we know. And this time we put here a static and chunk, so this will be properly one after another executed. But also says that once you define the result here in all of the different for loops parts of it, you also want to have the final result summarized from all of the different parts of the loops. Right? Otherwise, you would have more local basically result out of this. But as we basically want to have the result over all the loops, which are now, let's say, put into different pieces in the static, which in the end doesn't matter, but which matters for our result computation, then basically you can use this reduction clause. So let's have a look in it, how that works when we do the practical. So reductions. Also here, the reduction clause .c program is interesting. Again, no surprises. We have the overall number, we have a chunk size. We initialize a little bit here that we don't have everything 0. But here, as you see already, this is what I was alluding to. Here you see a nice break of a normally very long pragma statement, right? What you can do is another learning experience. We have the schedule static on the chunk size static, which means basically thread number by thread number accurately will be waited for and assigned the work. And of course, the most important here for the example is the result, because I added the result here again, and I write it in each of the different parts of the for loop, which is fine. So I add up essentially to the result, which is fine and can be still done in parallel. Also because I have these indices again, and you see it's basically again something which could be nicely parallelized. But in the end, I might be not interested in the selected results of the different loop parts. I want to have the final result over the whole loop. And this is then something where the reduction of the plus result here makes this actually happening. And you can imagine you can play with the operator here. It does not need to be a plus. It can be multiplication, maximum, and some others that are already well defined. By now, the submit script gets a bit boring. I guess all of you know that basically this is very similar. Still, you see in the basic things, you always do the arrows. You see my naming. I forgot again to put it to the reductions clause when I created this simple example. But again, we're staying on one node. We have 4 OMP threads that should be working on it, on this reduction clause. So let's look how that works when we SPatch it, because we also want to have a bit time still for the HPDB scan, which is a bit more elaborate, and we will see in some minutes. So we have executed it. It's already coming back with the answer, which is actually not much what we expect from this. In the end, it should be just the final result that is essentially standing here. So I think all of this is getting more and more very easy to you to understand, because the modus operandi of the similar aspects we do is very similar. We put a pragma statement, a sentinel in front of some to be parallelized region. This is in many cases in applications a for loop, but must not be. As you remember from some of the examples, that is an important takeaway message. So let's come a little bit also essentially to the idea of this clustering algorithm. Again, if I think about some of the office hours from students that don't know exactly what clustering is, don't worry, we will have it in lecture 10, a little bit reviewed alongside also the other elements of machine learning, which is classification, which largely stands for the point that if you have a new point, you basically learn what the other class representations are. And if you have a new data point, you can basically understand with a classifier if you have red or green point there. This is something we call classifications. Clustering is mostly like you don't know really these class identities, but you have some similarity measure, like the Euclidean distance here, for instance, in this example, where you would say and recognize that these could be clusters. And the clustering algorithms would use as density measures as an example, or similarity measures really, to identify those clusters. And then on top of that, you could maybe then do classification if you want. But it's another approach in machine learning, which actually has also quite some overlaps with data mining. So clustering in many cases is also considered as data mining technique and also a machine learning modeling technique. So from the regression perspective, this is more, let's say, a little bit trivialer, but still very powerful ways of doing machine learning, mostly for trends. Let's say the more money you put in TV advertising, the more sales you would get. Things like simple trends analysis, which need to be maybe not linear, but is essentially around identifying a slope in the data. But again, don't worry about this. In lecture 10, we will review this a little bit more. We have a complete lecture about it. We take this material up in subsequent lectures in neuroscience and remote sensing to really show you where machine learning is broadly used in high performance computing with this in parallel, and then essentially get a much better meaning from it. Still, I would remember you all that, of course, this cannot be a complete parallel machine learning course, right? So yeah, you have to really go to another machine learning course, learn the fundamentals, statistical learning theory, Wapnick-Scherbonenkes inequality, theoretical considerations, really why we can learn, what makes learning feasible, PAC learning. There are lots of statements and lots of interesting aspects that I also teach in different other tutorials on my website in the teaching area, if you want. But here, this is not really the core of the course. However, we want to show you some really practical examples, what we use in practice in science and engineering today. And clustering is here a good example. We created this HP-DB-Scan, which is quite a powerful publication these days, very often cited and often read. You can see it on ResearchGate, for example, which is really a parallel approach of clustering, distribution of data here, but using a very traditional algorithm called the DB-Scan algorithm, density-based one, which has some way of iteratively and essentially then extending always the clusters to a certain amount of so-called epsilon neighborhood, where there should be a minimum number point in the epsilon neighborhood to make it a cluster, and then some extension strategies. Also, this would fill a full lecture, so I cannot go into the complete details about it. So please be referred to this publication, for instance, to understand how it works. You can use it for different elements. This is the point cloud of Bremen that we use here in the practicals, but we also use it for brain scans. Basically, you see here a slice of a human brain with different cortical layers. Now, when you look into the different cortical layers, you see definitely a kind of different densities between the cell layers in order to identify these different colors here. So these colors were artificially added because essentially the clustering algorithm and the human would identify this. And here the idea is, instead of the human, the machine can identify it, so saving time for the human or for the neuroscientists. Now, when we look at this, it has a quite large software behind it. We do firstly an overlay hypergrid here, and some things I already have explained in previous lectures, so I make it a bit quicker here. We sort and distribute the points a little bit, and once we have them a little bit spatially ordered, we do performing local DB scans. And this is now the interesting thing where shared memory really plays a role. So you do this in shared memory, and then in Halo regions, which you know already from, kind of the distributed MPI fashion, you then would, across the different nodes, you would merge the halos with distributed memory with MPI. But if you just stay with shared memory, then you have, of course, two considerations. Firstly, it should be, let's say, really being able to fit all in your memory if you want to do just shared memory. And of course, the number of threads would be then essentially limiting, because you have just a limited number of CPUs that you can have for the node to spare, instead of being completely scalable and adding more number of cores, more and more and more. You see here essentially also the slope of essentially, or the kind of printout of the scalability behavior. With a hybrid code, we're having the best performance. That's why we pick it also up when we come to the next. Needless to say, MPI is here also shown, but OpenMP not, because we just don't scale very up. We need all the CPUs which we have in the shared memory not really existing. But let's go a little bit to this example when we want to, see some things happening. We see here HP-DB-Scan and the OpenMP. This time it looks a little bit different. We don't have a C code. Why is that the case? Because we have already encapsulated our source code into a load module area fashion. We also use HDF5, if you remember from one of our sessions. So we also have to load this as a dependency of the module, but we don't have really a C code instead, of our previous examples. Still, we keep the node to 1 and the task of 1, but we say we want to have 16 basically threads working on it. And this is also something that we have to put in the code here with -T16. More importantly, for data science methods like clustering and HP-DB-Scan is rather the data set. So you see essentially here that we have two types of data sets, a Bremen small and a Bremen big. So this means the following. If you look, this is just much more data. Right here you have the size of our Bremen small data set, while we also see essentially here the Bremen big data set, which would take much more longer, and we subsampled from there in order to make it also happening for basically tutorials and trainings to execute at all, because it would take much more time to do it than for this Bremen small, for Bremen large. So when we SBatch it, it is basically starting the job. We would assume now there's basically a QStat job that is running. And then this gives me the opportunity also to go back to the slides, because the interesting thing is, of course, this will take now quite some time. This is a really interesting algorithm. It is computation intensive, so it's not that we can finish this within the part of this lecture. But I still want to do a couple of points here. Firstly, this is exactly this job script that we just have seen. And you see it is running, and it will do so for around half an hour. And this is because we have 16 threads. And I brought you here an example from my previous runs where you have, for instance, here the interesting S-control command of the scheduler that we can also investigate now a little bit in essentially in our job here. We have S-control, show, job ID. This specifies your job ID, and we will say this is running, just to understand maybe a different way of how you can get more information for the job. So it's running, that's what we know, but we assume it will run only on one node. And here we have it. It's on the compute node, not anymore on the login node. That's also what we expected using the scheduler. We have the number of nodes equals 1, number of CPUs is 16, because now we are parallel in 16, but with different threads, right? And we stay on one node, which is very important here to make it then really the shared memory aspect. It is running. And essentially here you see again the job script that is related to it, where the output should be. And this is of course something which we maybe can already look inside. While QStat probably is still working on it, so we have just 1 minute. We have to also think about that maybe there's already something wrote to the file. We see here it's a 3210, and this is also the 3210 out. So we can essentially use this output and look inside. And what we see is there that already the pre-processing was calculating the cell spaces and so on, distributing the points. This is all done very quickly, also because we stay in shared memory. But here we do a local DB scan now. Now we're really doing the computing, the density-based clustering locally. Of course, here it's clear that it's locally because we have just one node. But here's now where the 16 threads are working. And the interesting thing is when you continue to do so, and you would have just 4 threads, you see you will run out of time if you, for instance, specify a wall limit of 1 hour. And of course, the code is available to you. I welcome every one of you to really use it. It is part of our assignment 3. And essentially, you can just reproduce this. When you put the wall time 1, you will see with 4 threads, we're still not there. So you just change here essentially the CPUs for tasks and the threads. Also here, it will take so long that essentially you don't get anything, let's say, done in this hour. As you know from one of the previous lectures, we talk about that the job runs against the wall. Now, if you increase the wall time, that will also not really helpful, because we just see that actually with 4 threads, you're just too slow. You need more power, more computing. And that's why we extended to 16. Now we have 16 threads. And you will see once you execute it, again, it will take, you see here in our last run, it takes 31 minutes, right? So I cannot really finish it here in the lecture. But to show you that this is really working, I can go into one of our previous runs here, where we essentially see, for instance, here, that after this local DB scan, the merging of the neighbors, there are no neighbors, right? Because we are just in a shared memory space, right? In MPI and so on, the merging the neighbors is not possible, not necessary, because we're just within one node. And Bremen small actually fits in and works and generates here 21 clusters. So this is finished, but it also took a total of 1,887 seconds. So if you divide this by 60 seconds, you will come basically to the half an hour we were alluding to, so 31 minutes or so. And of course, this is just a start. In the next lecture 7, we will talk about when we do it hybrid, then we will increase the number of nodes here to 2, for instance, and then having more threads available to work on the problem. In parallel, we have to have also then more nodes available, like 2. But this is something really we do in the next lecture. Then you can imagine already it's getting more and more complex to program all of this. So essentially, I'm talking about really debugging and understanding your code better. And then on the other side, what you also want to achieve with this maybe is a performance increasement. So you use performance analysis tools like essentially Vampire or Scalaska to really understand OpenMP and MPI tools. There will be a complete lecture about this, how you can basically also identify several certain things like race conditions and so forth. And of course, something important to see that you need much more stronger tools, because if you do PS here, for instance, on the nodes, you can just basically quickly show you this. When you do PS here, you see that just bash and PS is running. So although we see in QStat, there's HPDB scan running, but now what's the problem with it? We are here on the login node, right? Of course, here's no process of HPDB scan. It's running on, as we know from our S control statement, right? Show the job ID here. It's running not on the login node, it's running on the compute 2.0, on the compute node as it should be. So that means also we need parallel performance analysis tools and profile mechanisms for debugging, for analyzing and monitoring that actually work with this parallel environment. It's much more complex than just doing a PS, for instance. And then, as I was saying also at the beginning already, just repeating, OpenMP is strong. MPI together with OpenMP is even stronger. But what people really start now in the last, let's say, 5 to 10 years is now more and more accelerators usage. And this always basically refers to something like you have at the host CPU an accelerator attached. Could be an NVIDIA GPU that you already know, maybe from the previous times, from Pascal, Volta, basically to the new generations of A100s, which have extraordinary performance. And we will show that a little bit in our deep learning lectures and remote sensing lectures. So, but still, this is of course a new paradigm you have to combine with it. Still, you see that people have actually looked at OpenMP and thought they could really earn something and basically derive something from it. So we will see that OpenAC, you see here, pragma-ACK statement, the parallel loop, and copy out and so on for basically getting data from the main memory to the device memory and so on. FOSSI accelerator here, for pragma accelerator, is very similar than OpenMP, right? So it supports now GPUs as well, but it would be too much in all of one lecture. That's why we will have lecture 9 again when we come back to this relationships of OpenMP and GPUs together. So that's it again for the lecture today. I'll leave it again to show you that, of course, this job is still running and will be taking around 31 minutes, but you have the slides and can also use this parallel implementation on your own, play with it, maybe increase the number of threads to really use it in practice. The source is open source. You can just use it for any application domain problem, and it scales quite well. Of course, being limited with shared memory. If you really want to scale high, you have to do hybrid. That's what we do basically in the next lecture.